introducing the concept of having a non-trivial bundle. So the idea was you have some manifold with various coordinate patches. And in each coordinate patch, you had some gauge fields, AI, AJ, AK. Now, when we go from patch on the intersection, AI, AJ are related by some gauge transformation, Xij. And similarly for AI and AK are related by Xik, and AJ, AK are related by Xjk. And there was an important condition, which was if I start in patch I with my gauge field AI, and I want to relate it to the gauge field in patch K, there's two ways to do it. I could just go directly, like that, or I could go via Uj. So, and we wanted those two different gauge transformations between AI and AK to be the same. So that meant we need that Xik is equal to Xij, Xjk. So let me give you an example of this kind of thing. The example I'll give you, this particular equation turns out to be trivial. We take our manifold to be the two-sphere, which is we view as the complex plane union infinity. We take U1 to be the set of points Z where the size of Z is less than 2. And U2 to be the set of Z where the size of Z is bigger than 1. So this is what it looks like in the complex plane. But if I was to bring it back to the two-sphere using the stereographic projection, you would find that the two-sphere looks like this. The north pole gets mapped to infinity. And I have these two circles. But this region here, everything below this, this tropic is U1, and everything above this one is U2. So clearly, the intersection, the region they have in common is this region near the equator, which forms like an annulus, a little band. So U1 intersection U2 is the set of Z, or 1 is less than Z is less than 2. So we're going to build a collection of gauge fields and gauge transformations to glue them together. So I'll take my group to be U1, so that the gauge fields just have no interest in the algebra index. They're 1-by-1 matrices. But the gauge transformations, Xij, these can be thought of as complex numbers of modulus 1. So what do I do? So I'm going to declare that on this region here, my gauge field is 0. So we declare A1 is equal to 0 And then the interesting part will be what is x12. And I'm going to write this as a function of or and theta. I'm going to take this annulus here in polar coordinates, where 1 is less than or is less than 2. And I'm going to choose this to be e to the 2 pi I n theta. Which is certainly a complex number of modulus 1. But then we have to think about what is A2. Well, A2 is going to be determined by the fact that it's related by a gauge to A1 by a gauge transformation. So on the region where 1 is less than or is less than 2, A2 must be x12 inverse dx12, which is, if you calculate what you get, 2 pi I n d theta. Okay, so that's good. So we know what it is here. It's like the angular form for along this circle. But what happens when I go off towards infinity? I can't really, the form d theta doesn't really make sense at infinity because the coordinate theta doesn't make sense. So what you have to do is you make it get small in this region here, to make it get smaller. So to define A2 when or is bigger than 2, we choose some function of the radius, with f of or is equal to 1, if 1 is less than or is less than 2, and f of or is equal to 0 for a very large radius. And then A2 globally is f of or 2 pi I n theta. So this makes sense. When or is finite, this is perfectly fine, but when it goes off to infinity, it tends to 0. So this is a perfectly fine gauge field on the region where or is bigger than 1. Okay, any questions? So we can ask, so we're going to keep this example in mind, and let's ask the general question. When is it possible to choose a new gauge so that our gauge fields are actually globally defined? Question in general. Can we find well, there's a general answer, which we'll maybe might discuss in a minute. But for this case, for the case of an abelian gauge group, wow. We consider the curvature FAI So this is a gauge covariant quantity. So under a gauge transformation, FAI gets sent to, xji inverse FAI xji. But in the abelian case, I can just move this over here and they cancel. So if I have a gauge field defined on patches with gauge transformations relating them, then the curvature is globally defined. They just agree on the patches. So FAI is just equal to FAJ on the intersections. So this is a global two-form. Now, if there was a new gauge in which my gauge field was defined globally, let me see. So if there was a new gauge where AI tilde just equal to AJ tilde on the overlaps, then, while the curvature of the original connection is going to equal to the curvature of in the new gauge, because it's a gauge covariant quantity. But because this is a global expression, this is just dA tilde. Because the curvature for the group U1 is just the de Rham operator. So if I could express my gauge field globally, then this two-form is D of something. That implies that the cohomology class in H2 of M is equal to 0. And this happens if and only if the integral of f of A over every closed two-cycle okay. So any questions?
Basic question. What do you mean by a gauge transformation?
Well, so it's easy to talk about a gauge relative to another gauge, in which case it's a gauge transformation. So we started off with a gauge that was like, because we had written on each patch, we had written a particular gauge field.
It's like the set of gauge fields that you choose on each patch.
Right. So if I choose a gauge, then I can represent on each patch my field by an actual gauge field. Well, in a different gauge, they'll be related by some gauge transformation. So when I say in a new gauge, I mean, what does it mean to choose a new gauge? This means to choose some xi on each patch so that AI tilde is equal to xi inverse the xi. So in this case, that's plus AI, because it's a gauge. So the question is, can we find some gauge transformation on each patch such that the AI tildes actually agree on the overlap. And what we're finding is that the curvature is an obstruction to doing that.
What is a closed two-cycle?
So that's, in my space, that's some two-dimensional subspace with no boundary.
So this only happened for a billion case. For that, you're just saying f is equals to f of a is equals to d of a.
Yeah.
That means the bracket vanished.
That's right. So in the
That means it was a billion.
yeah, this only happens in the abelian case. Like in the non-abelian case, it's quite a bit more subtle.
But you still have the bracket vanishes.
No, I mean, see. Well, in the non-abelian case, the curvature is a gauge covariant quantity, not a gauge invariant quantity. So that means that it has some Lie algebra index. So I can't just build. If I want to build a cohomology task on the curvature, I have to do something to that Lie algebra index. Like I do. So there's extra. So there's no simple process to go from here to a cohomology class. Like the curvature is like a matrix value to form. And maybe I take its trace. Maybe I take some power of it and take its trace. And that will lead you to what are called characteristic classes. Okay, so let's quickly check. In our example, were we able to do this? Were we able to find new gauge transformations in each patch so that it glued together, so that our gauge field had a global representation? So we can do that. Being able to do that means the bundle is trivial. Well, to do that, we need to calculate the curvature here. So let's look at the curvature. So we have a formula for our gauge field, and so what we're going to do is calculate the curvature and then integrate it over the two-sphere, and we will find something non-zero. So in the S2 example, A is on the patch f of or 2 pi I n d theta for or bigger than 1, and A1 is equal to just 0 on the patch or is less than 2. Now, of course, these are not equal, but the curvature we're going to build from them, because curvature behaves well under gauge transformations, the curvature, which is just the de Rham operator applied to these guys, will be equal. So obviously, dA1 is equal to 0. So the curvature vanishes in the region or is less than 2. But what's dA2? Well, that's minus f prime of or 2 pi I n d theta d or. So let's check that they agree on this region. Well, f had the property that if or was less than 2, it was constant, so its derivative vanished. So we know that this is equal to 0 if or is less than 2. So this expression here is the curvature. Now, what is the integral of the curvature? The integral over the two-sphere of f. It's convenient to do this integral in polar coordinates. It's just an ordinary two-dimensional integral. So I'll get a factor of minus 2 pi I n. The integral from theta goes from 0 to pi of d theta. No, hold on, theta period 1, isn't it? And then the integral from or equals 0 to infinity of f prime of or. What's that?
Sorry, what? The theta, the upper limit of theta is pi or 2 pi?
No, I chose theta to have period 1, right? Because I had the gauge transformation to be e to the 2 pi. You wouldn't get a pi squared here.
Yes.
Well, I'm going to write this integral as an integral from not from 0 to infinity, because this guy vanishes when it's less than 2. So say 1 to infinity. Now we integrate by parts. So f is equal to 1. Let's say whatever, 2 to infinity. When or is equal to 2, equal to 2, and f is equal to 0 when or is equal to infinity, so that this expression becomes minus 2 pi I n. So that the integral of the curvature, maybe I picked up another minus sign here, I think. The integral of the curvature really does not vanish. So let's think about another way to see the same thing, because it's going to be really useful. So unless there's any other questions?
From r equals 0 to 1?
Well, this function f takes constant value in the region 1 to 2, so f prime is 0. Like the curvature so here, the curvature in the region when or is less than 2 has to be 0, because my gauge field in one gauge was 0 there.
Okay.
And it is because this function f is constant in that region. So the slightly tricky part of doing this is that I'm doing an integral of something which is represented as a derivative only for part of the region of the integration domain. For the other part of the region, it's 0. And we see something fun here, actually, which we'll get a better understanding of later, I hope, is that you notice the integral of the curvature, the only values it takes is 2 pi I times an integer. So this integral of the curvature is quantized. So let's look. So in general, if we have ai on each patch and xij, which are gauge transformations, we can ask, can we find xi so that if I define ai tilde to be xi inverse exi plus xi inverse aixi. So can I find a gauge transformation on each patch such that in this new gauge, the ai tildes, where ai tilde is actually equal to aj tilde on the intersection? And the answer to this question if and only if we can find such xi so that the gauge transformations of the overlaps are written as x. Is it xi inverse xj or xj inverse xi? I can't remember. The gauge transformations of the overlaps are written as xi xj inverse. So why is that? So suppose I have an expression like this. This is actually some little calculation. If I have an expression like this, so then if this is true, and then we define ai tilde by that formula, then the equation that aj is equal to xj xi inverse dxi xj inverse plus xj xi inverse ai xj inverse. So this equation, by moving some of the xj's to the left-hand side, implies that xj inverse bxj plus xj inverse aj xj equal to x dxi. So this is some little calculation. So, from this point of view, let's check that we can't actually do that. Well, we know we can't, but let's check it in another way, so we get, which I feel gives you maybe more feeling for it. So again, we have the two-sphere. This region is U1. This region is U2. And x1, 2 of or theta is e to the 2 pi I n theta. So can we find x1, which are maps from the region where from the, U1 to the unit circle. And x2 from U2 to the unit circle, so that x1, 2 is x1, x2 inverse. So the intuition for why you can't do this and see if we consider x1, 2 of or theta as theta ranges from 0 to 1, which is its period, this guy, it winds n times around the origin. It's this complex number. This should be a very familiar thing from complex analysis. It winds around the origin n times. But since U1 is a disk, for any x1, U1 to the circle, x1 cannot wind around the origin at all. So, draw a little picture. This is U1, it's a disk. I have some for every point in this disk, I'm associating a point in the circle. And if I try to imagine how many times it winds around the boundary, well, as I bring this in, that's a discrete quantity. It can't change as I bring it in. But at the origin, it doesn't wind around at all. So that number must be 0. A more formal way to say this is that the winding number is the integral around the boundary of this disk of dx1 over x1. Then I'm viewing it as a complex number. This integral is a standard way of representing the winding number. Because this guy is the pullback of the volume form on the circle of the target. And this is, by Stokes' theorem, the integral over u1 of d of dx1 over x1, which is 0. This equality is Stokes' theorem. But I like the intuition by thinking about winding numbers. It tells us that this guy can't wind around at all, this guy can't wind around at all, and this quantity winds around n times. So it is not possible to solve this equation. And we're seeing the issue is to do with the topology of the circle. Okay. Any questions about this? Yeah.
Is it a special case of a non-trivial bundle in the sense that we cannot have a non-trivial bundle on S2? Because I mean that this xi and xij is a special case of the non-trivial.
Are you saying, are there like other non-trivial bundles on S2?
Yes.
Okay, so if you take this analysis further, you will find that the collection of non-trivial U1 bundles is labeled by the integers and is captured by the winding number of the gluing function, x12. If I took some other group, what we're going to find is that the gluing function is a map from the circle to that group. So we're going to be studying the fundamental group, whatever my gauge group is. So for the group SUN, there are every bundle has trivial topology. For the group PSUN, there's n different ones. Does that make sense to you? I mean, for example, SU2 is the 3-sphere, but PSU2, which is SO3, is a quotient by identifying opposite points. So SO3 is fundamental group Z mod 2, so I did a spin. So there's 2 non-trivial SO3 bundles on the 2-sphere. Let's see, where we go. Oops. So let me finally introduce the Chern-Simons Lagrangian. And I'll introduce it in the way, there's a simple formula which is defined in the case you have a global gauge field, but there's a kind of clever thing you can do when you don't have a global gauge field, and I'll do the more clever thing first. So let's start. Well, let me write it out for an arbitrary for the group SUN or UN. Suppose we have a gauge field. So then on each patch, we have the curvature. Which is an expression like this. And write like this, where A is a Lie algebra index, and MA is the corresponding element of UN. So I'm choosing a some basis of the space of n by n Hermitian matrices. And the curvature is gauge covariant. On the intersection, Faj is equal to Xij inverse Fai Xij, which this expression is very simple. It literally means I'm conjugating this matrix. So this is a two-form with entries and matrices, a two-form. When I expand it in terms of a basis of matrices, each piece is a two-form, and I'm just conjugating those matrices. So we can build gauge invariant quantities by using traces. If I have a trace, these conjugation factors will drop out. In particular, we can define Fai wedge Fai, the trace of this guy. What does this mean? I expand this in terms of matrices. The sum over AB, the Faia wedge Faib times the trace of the corresponding matrices, of the product of the matrices. Okay. So this expression turns out to be gauge invariant, meaning it's the same on any two coordinate patches. So I wrote a homework for this week which involved this expression. So it appears in lots of places in physics. In particular, in some people study the axion field, and they study dark matter. The axion field is coupled to this. It's a scalar field coupled to this expression. Okay, so as I said, we can check. It's easy to check. that this is gauge invariant. There's really nothing to say. We look at the expression up there for how the curvature transforms under a gauge transformation. And you do a gauge transformation, and I just have x inverse x, x inverse x. And the things here cancel, and the things at either side drop out because I'm taking a trace and I can move them around. That's very easy. So if M is a 4-manifold, then trace f wedge f, which is a 4 form, is a Lagrangian. And we can consider the integral over M of trace f wedge f. Right, so I've written it on each patch, but the point is that gauge invariance means that the Lagrangian agrees on overlapping patches. Okay, so let's see. If M is a closed 4-manifold, meaning it has no boundary, then integral over M of trace f wedge f does not change if we vary the gauge field a little. By small amounts. So it's a kind of a funny Lagrangian. It doesn't depend on the small variations of the gauge field. It only knows about more global topological properties of your gauge fields. Let me maybe explain why that happens in the abelian case. So in the abelian case, so I'll just assume there's one gauge patch for simplicity. If I vary A to A plus delta A, then since the curvature is just dA, integral the variation of integral dA wedge dA I didn't prepare this far, so maybe this is it. Variation is this argument is too sketchy because if I assume I only have one global gauge patch, the whole quantity is a total derivative. But there's some similar argument where in each patch you vary the density and it varies by a total derivative, and you have to check these total derivatives glue together in a nice way. So yeah, I didn't do that very well.
Why is that a total derivative?
Because d squared is 0. It's like d of that, and this is over there. So another important property. So we saw in the abelian case, or at least we calculated, that the integral of the curvature appeared to be quantized. And this expression is also quantized. Integral over m trace f wedge f is quantized. So it takes values in something like 4 pi squared times the integers.
I'm sorry, I'm super confused.
Sorry.
Is that this action looks exactly like the Yang-Mills action that we've studied, and that has non-trivial equations of motion.
Okay. Thank you for asking that. The issue is this wedge. Like if we were to write things out, let's write this out in coordinates, and you'll see that it's different. So the integral over m of a local patch dx1 wedge dx4, the trace there's some expression from the trace for the color index. And here I have f a I1, I2, f b I3, I4, epsilon I1, I2, I3, I4. So the difference is this epsilon tensor, not present in the Yang-Mills action. Instead, in the Yang-Mills action, you're raising and lowering these indices using the metric. So that's what makes this one much simpler. So I should give you some kind of homework about some calculations about that kind of thing. I'm sorry, I'm running a little bit out of steam because I got further than I thought I had when I prepared. So let me finally write down what the Chern-Simons action is in the clever way. So if I have a 3-manifold, and M4 has boundary, N3, and if we choose a gauge field, on N3, and we extend it to M4, then the Chern-Simons action of my gauge field in its integrated form is defined to be the integral over the 4-manifold of the trace of f of a, like f of a. This seems a little weird because it's not a priori the integral of some Lagrangian over the 3 manifold. And you might worry about how does it depend on this choice. But then there's this fun fact. Because for a closed manifold, this expression is quantized. The action functional does not depend on this choice. So let's see why that is true. So if M4 tilde also has boundary N3, then we can form a new manifold M4 tilde. I glue them along the boundary. We call that X. This has no boundary.
Sorry, I lost the relation between tilde and then just n. Sorry.
What's that?
N tilde just n. What's the
M tilde and M are 2 different 4 manifolds with the same boundary.
Okay, okay.
So you draw a picture. Let's draw a picture in 2 dimensions down. This is draw it as a circle. This might be something like that. And the other one is some other manifold. Maybe it's more complicated. But they have the same boundary so that we can glue them together into some big thing. Now, we can compare. When we glue, there's some change of orientation. So the integral over x of trace f of a wedge f of a. We're careful about the signs. It's the difference between them. Because in the beginning, really, I had two manifolds which bounded this guy from the same side. But to glue them, I had to flip one the other way. That changed the orientation and picked up a sign. Further, this integral is quantized. So therefore, e the I, I'm probably not going to get the factors of pi right. This is quantized value something like 4 pi squared. Maybe that should be 8 pi squared. I think that should be 8. Although I'm a bit unsure. So e to the I k over 4 pi of the integral of m4 trace f wedge f. If we look at this expression, if I choose a different 4 manifold, bounding my 3 manifold, this thing changes by 8 pi squared times an integer. So if I divide it by 4 pi, and I have I and k is an integer, it's going to not change at all. This is independent of the choice of M4. Okay, so we conclude so that the Chern-Simons Lagrangian defined as integral over 4 manifold of trace f wedge f makes sense if we included, if we study the path integral gauge fields e the ki over 4 pi Simons, where k is an integer. And this quantity k called the level. Okay, so I know this was a bit subtle, but are there any questions? This trick of writing a Lagrangian in dimension d in terms of a Lagrangian in dimension d plus 1, which is quantized on closed manifolds, is something Witten uses all the time. There's a bunch of Lagrangians which arise this way. Another famous example is the Weissymino term in two-dimensional sigma models.
Sorry, I don't understand. What's the meaning of introduce this big X manifold? So what do you want to say about it?
So the only reason you introduce this X manifold is as an intermediate step to check that when I change m to some other m tilde, I will change this quantity by some integral amount.
So it is quantized no matter it has boundary or not has boundary.
Well, the integral of f wedge f is quantized only if I have boundary.
Nice.
But if I don't have boundary, it's quantized by like 8 pi squared z if I don't have boundary. But if I have boundary, it's not quantized, but it's like determined by something on the boundary 3 manifold plus some integral stuff.
So we started by choosing a gauge field on the 3-dimensional manifold, and then you say we extend it to M1.
Yeah.
How is that done? How do we extend it?
Okay, that's a good question. So the tricky part, it's not obvious you can do this, right? So we for example, we chose a U1 gauge field on the 2-sphere. That can have the property that its curvature is non-trivial integral over the 2-sphere. Now, that tells us that we can't extend it to a U1 gauge field on the 3-ball by Stokes' theorem, because I would pick up, because the 3-ball is no interesting topology. So there's so to show that you can do this, there's a little bit of topology involved to show that you can always do this. That's not quite obvious. So part of the argument is also it doesn't matter how you extend it. Because if I choose a different extension, the same kind of trick will say, well, the Lagrangian I wrote down changes the chips by an integer. Okay. So, but as I said, you don't have to really understand all the details of this presentation. So this presentation of the Chern-Simons Lagrangian is kind of useless for perturbation theory. There's a formula that is great if you work in perturbation theory near your trivial bundle. But when Witten was writing his stuff, he really wanted to have a more global thing for all gauge fields, and then you need to do this kind of thing.